Hello everyone, I am Honak, a PhD scholar at IIT Kanpur. I am the TA of the course Fundamentals of Supersonic and Hypersonic Flow. I will be taking the weekly live session classes. Today is the first session of the problem solving session, and in this week mainly the fundamentals were discussed and what are the things which are required for the course. First we will discuss what is perfect gas. So perfect gas is the one in which intermolecular forces are neglected. We also neglect the size of particle. We don't consider the size of particle. We consider that the volume of particle is negligible. And we also consider that there is no intermolecular forces between the two molecules. So if gas is perfect, then we can write one equation which is given by PV equal to mRT, where P is pressure, V is volume, M is the mass, R is the specific gas constant, and T is the temperature, which is also equivalent to N R bar T, where N is the number of moles, R bar is universal gas constant, which is multiplied by molecular, which can be written as R bar equal to M bar into R, where M bar is molecular mass. The value of R bar is always constant, which is given by 8314.3 joule per kg mole Kelvin. We can get this equation from this also. If you see mRT, if we divide by molecular mass and multiply by it, then you can see this M bar R can be written as R bar, and M by M is nothing but number of moles. Like this we can derive it. This perfect gas equation can also be written as many different forms. One of form is P equal to rho RT. How do we get it? Let's come to this equation. PV equal to mRT. If we divide both sides by V, then left hand side will become P and right hand side, if we see M upon V is what? Density. So it will become rho RT, where rho is the density. Now we will see one problem related to this perfect gas equation. Density of a fixed mass of a gas can change if often A, volume remains constant, often B, pressure changes, temperature remains constant, often C, volume changes, often D, pressure and temperature remain constant. What will the answer for this question? There can be multiple options also possible here. Okay, we'll solve it. So what is our density? Density of fixed mass. So mass is fixed. So density can change when. So first we'll see how can we write density. So density can be written as M upon E, rho equal to M upon E, where V is the volume. Now we have fixed the mass. So if we want to change the density, how can we change the density? We can change only if V is changing. So if volume changes, it means density also changes. So option C is correct. Now if you see A and C, both are the opposite of each other. So A is also not possible. In option B and D, it talks about pressure and temperature, but in this equation there is no pressure and temperature. So let's assume that gas is perfect gas. So for perfect gas, what is the equation? P equal to rho R T. So how can we rho written? Rho can be written as P upon RT, where R is constant. Okay. So often D talks about pressure and temperature remain constant. If let's say pressure and temperature both are constant, then density will also be constant. So option D is not possible. And if only temperature remain constant, then for density to change, what should change? Pressure should change. So option B is correct. So in this problem, option B and C are correct. Now we will see what are the different view for the problems, or in how many ways gas can be studied. One is the microscopic view and other is the macroscopic view. In microscopic view of the gas is taken as collection of particle. Gas is taken as collection of particle, and all particles are going in random motion. And if we combine the kinetic energy of each particle, then it will contribute to the overall energy of the gas. So let's say there is one particle, it is doing the translation motion, so it will have kinetic energy, translational kinetic energy. But if particle is molecule, then it will also have rotational and vibrational motion, which will also contribute to the gas energy. Let's say there is one molecule, so it can rotate about one axis, so it will have rotational kinetic energy also, and this molecule can vibrate about this axis. This molecule can vibrate, or both particles can vibrate, so it will also have vibrational energy also. Finally, if you see one atom or molecule, it will have electrons. So if it has electron, so that electron also has the motion. So due to the motion of electron, it will also have electronic energy. So in how many form the energy of gas can be? Energy of gas can be in the form of translational energy, rotational energy, vibrational energy, and electronic energy. These two are present only for molecules, rotational and vibrational energy. Translational and electronic are present for both atoms and molecules. The system will be in equilibrium if particles are in the state of maximum randomness. Only when maximum randomness is present, only then will be the equilibrium of the system. Now we will see macroscopic view. In macroscopic view, gas is viewed as the continuum. So in continuum, we have seen the microscopic view. So in macroscopic view, let's say if we are taking small, very small volume. So if we take the volume, even if we take here, 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 or if we started decreasing the volume, then at 1, let's say density is given by limit delta V tends to 0 m upon delta V. So if we plot this density in delta V, then if we start reducing it, then there will come a time when density will remain constant. It will not change. And if we are able to achieve that, it means that flow is in the continuum. And let's say there are very less particles. So if we are taking the, let's say this big size, we might be able to get one particle and some density. But if we are taking small enough, then there might not be any particle inside. For the, like for the fairer rarefied flow, in that case, there will not be continuum. So for continuum to exist, the mean free path is the path average path traveled by particle before the successive collision. So when mean free path is very less compared to dimensions of the flow, then flow will be in continuum. And we can find equilibrium if there is no gradient in flow properties like velocity, pressure, temperature, and chemical concentration also throughout the system. That is, system has uniform properties. For an equilibrium system of a real gas, where intermolecular forces are important, and also for the equilibrium chemically reacting mixture of perfect gas. When real gas is there, or when we are taking the equilibrium chemically reacting mixture of perfect gases, the internal energy is the function of both temperature and volume. If this is the case, then internal energy will be the function of both temperature and volume. Or you can say that internal energy is the function of two state properties. Temperature and volume are state properties. Similarly, enthalpy also will be the function of two state properties. If gas is not chemically reacting and if we ignore the intermolecular forces, then system is thermally perfect gas. And if it is only thermally perfect gas, then internal energy and enthalpy are function of temperature only. Besides this, if specific heat of volume and if at constant volume and specific heat at constant pressure also are also function of temperature only. So if we are writing like say dE equal to Cv dt, then it is equal to Cv function of T dt, or dH equal to Cp function of T dt. If these specific heat are constant, not the function of temperature, then system is calorically perfect gas, where E equal to Cvt and H equal to Cpt. But if we see from here, this dE equal to Cv dt, if we take the integration of this, it will be integration E naught to E dE 0 to T Cv dt. If you this is CV is constant, it can come out. So its integration will be E minus E naught equal to CVT. At t equal to 0, it is assumed that there is no internal energy. So E will be equal to CVT. Similarly, H equal to CVT. Is there any doubt in microscopic and macroscopic view? If no, then now we will see the fundamental law in the thermodynamics. First law of thermodynamics. It is very important law, and it is based on conservation of energy. In simpler word, all the energy of the system is conserved. And in other words, it can also be said that sum of the work done on system and heat added on system is equal to change in internal energy of the system. So let's say there is one system and we are doing some work on that and we are adding some heat. Del Q heat and del W work. So sum of this del Q and del W will be equal to the change in internal energy of the system. This first law of thermodynamics is written for the closed system. What is closed system? When there is no heat, there is no mass and energy transfer between system and surrounding. When there is no mass transfer with surrounding, but energy transfer is possible. For a given differential change in internal energy, there are in general an infinite number of different processes or ways by which heat can be added and work can be done on system. So one first thing to know first is that internal energy is a state function. So at a particular state, internal energy will not change. So let's say there are two states, 1 and 2. So we can go many different ways from 1 to 2. So those are the and these ways are infinite. So there are infinite number of processes. This is the process in which we can add and the heat and work, but internal energy will remain same. We can write this first law of thermodynamics for different kinds of process. There are infinite number of processes, but we define some simple processes. So first is the adiabatic process. In adiabatic process, there is no heat transfer. There is no heat transfer means del Q is equal to 0. So how can we write the law of thermodynamics? First law of thermodynamics, del Q plus del W equal to dE. If del Q is 0, it means del W equal to dE. Second process is reversal process. In reversal process, there is no dissipative phenomena. That is, there is no effect of viscosity, thermal conductivity and mass diffusion. So if let's say we reach from one state 1 to state 2 by some process, then we can come back through similar process to state 2 to state 1, and there will not be no losses. Losses are the dissipative phenomena. So in that case, work done will be equal to minus PdV. So if work done is minus PdV, then from the first law, del Q minus PdV equal to D. If we combine these two adiabatic and reversal phenomena, then the process is called isentropic process. So in isentropic process, it is both adiabatic and reversible. It means that from this adiabatic process, del W equal to dE, and from reversible process, del W equal to minus PdV. So if we combine both those two, then we will get minus PdV equal to D. Any doubt till now? Now we will see the second law of thermodynamics. The second law of thermodynamics gives the direction to the process. So it states that the change in entropy during any incremental process is equal to actual heat added divided by temperature plus a contribution from irreversible dissipative phenomena of viscosity, thermal conductivity, and mass diffusion occurring within the system, D as irreversible. These dissipative phenomena always increase the entropy. So entropy always increase because of this dissipative phenomena. So how do we give the change in entropy? ds equal to del Q upon T due to heat addition plus ds irreversible. Now this dissipative phenomena always increase the entropy. So ds irreversible will always be greater than or equal to 0. So ds will also be greater than or equal to 0. So the process will happen only in the direction in which ds is always greater than or equal to 0. If in any direction ds is less than 0, then that process will not happen. That is the second law of thermodynamics. That's how it gives the direction to the process. Now we will see some important relations. First is the TdS equal to dE plus PdV. We'll write this also. So one more thing I forgot. Let's say this ds irreversible is 0. It means there is no irreversibility. So process will be reversible. So ds will be del Q reversible upon T. So for reversible process, del Q is equal to TdS. So this is for reversible process. So from the first law of thermodynamics, del Q minus PdV equal to dE for reversible process. So del Q will be equal to TdS. So it will become TdS equal to dE plus PdV. So we got this equation. Now H equal to E plus PV. So dH will be equal to dE plus PdV plus V dPV. And dE is equal to, from this we can find TdS minus PdV plus PdV plus VdP. So these will cancel, and VdP we can take that side. So TdS will be equal to TH minus VdP. Now let's find out this formula, entropy. So here you can see this is in terms of pressure and temperature. So we'll use this relation. If we divide both sides by T, then Ts equal to, and one more thing, dH is nothing but Cp dt. This relation is for calorically perfect gas. So for calorically perfect gas, the Cp is constant. We will substitute this relation here. So we will get Cp upon T dt minus B upon T dP. One more thing, EV equal to RT. This V is volume per unit mass here also, everywhere. So V upon T is nothing but R upon E. We will substitute this also here and take the integration. So integration ds 1 to 2 equal to Cp is constant, so we can take it out, dt upon T T1 to T2 minus mu upon T is R upon P, and R we can take out, dP upon P P1 to P2. If we integrate it, we will get S2 minus S1. This we will get dt upon T log is, its integration is log T. If we substitute limits, then we will get Cp log T2 upon T1. Similarly, dP upon P integration is log P, and we substitute the limit, then we will get minus R log P2 upon P1. This second part we can get directly by substituting pressure in terms of specific volume V, or we can solve this first equation to get this form. Now let's say if process is isentropic. In this one, process is isentropic, then this is for isentropic flow. If process is isentropic, then S1 equal to S2. We substitute it here, then Cp log T2 upon T1 equal to R log T2 upon P1. Here it is not given, but Cp equal to gamma R upon gamma minus 1. We will substitute it here, so this R will cancel. So we will get gamma upon gamma minus 1 log T2 upon T1 equal to log P2 upon P1. So which can be written as T2 log log T2 upon T1 to the power gamma upon gamma minus 1 equal to log P2 upon P1. If we remove the log, then we will get P2 upon P1 equal to T2 upon T1 to the power gamma upon gamma minus 1. Any doubt till now? Then we will see what is compressible flow. So this is the flow in which density of the flow is not uniform. From compressible itself also you can understand something which can be compressed. So compressing means that density is not constant, it is not uniform. It means density varies and it is not constant in such flows. So generally, there is no flow in which no fluid which does not compress. So ideally there is no, in actual there is no incompressible flow in the world. But generally if density change is less than 5%, it is very less, low change in density, the flow can be considered to be incompressible. So we use one parameter, compressibility, tau beta, which will tell you about the fractional change of specific volume of the fluid element due to high applied pressure change. So what is fractional change? Dou v upon minus v upon dou p, tau beta. And inverse of this compressibility is known as bulk modulus, which we denote by K. So here this specific volume is given by 1 upon rho. So we can substitute it also here. So dou v equal to minus 1 by rho square dou rho. If we divide it by nu, we'll get minus dou rho upon rho. So if substitute it here, we'll get dou rho upon dou p, rho, 1 by rho dou rho upon dou p. It can also be written 1 by rho a square. This we'll see next how. Here this a is nothing but speed of sound. So now we'll see what is speed of sound. So what is speed of sound? Speed at which a small pressure wave propagate through the compressible medium is called speed of sound in that medium. So if some pressure is applied, then one wave will travel through the medium. That it is very low in strength. Its strength is not much, and the speed at which it travels is the speed of sound. So this speed will depend on the compressibility of the medium in which it propagates, and it is given by a equal to under root dou p upon dou rho s. This s means this is found at the isentropically. And for perfect gas, if you see this dou rho upon dou p upon dou rho, here we have derived this equation. From this you can see P upon rho gamma equal to constant. So let's say there is P upon rho gamma equal to constant, and let's take the derivative with respect to rho. So dou p upon dou rho to the power gamma minus gamma p upon rho to the power gamma minus 1, sorry, gamma plus 1 equal to 0. So this we can get dou p upon dou rho equal to gamma p upon rho. So if we substitute it here, we'll get a equal to under root gamma p upon rho, and this p upon rho is nothing but RT. So we'll get rho RT under root gamma RT. These relations are very important, which will be used many places. So it is advised to remember all this formula. Now we got this under root dou p upon dou rho equal to s. So what is a square? A square is nothing but underroot, oh sorry, dou p upon dou rho. So here we can substitute dou p upon dou rho by a square, so we will get it tau beta equal to 1 upon rho a square. Now we'll see one of the important non-dimensionalized number in compressible flow, which is Mach number. So this Mach number tells about the domination of fluid particle inertial force over elastic force. And this elastic force is the force which is responsible for the propagation of pressure waves across a medium. So m is given by under root inertial force upon elastic force. Inertial force is given by rho a u square. Rho a u square is nothing but dp by dt. If we see force, it is nothing but dp by dt, where p is momentum. So this p is given by mass into velocity. So to write this mass into velocity, and this mass is nothing but density into volume, and this volume, as this mass is changing, so this you can write it as rho u square, v square or u square, velocity whatever you take, because mass is changing. So rho a u square, and elastic force is nothing but k into a. K is the modulus of bulk modulus, this k, which is given by rho dou p upon dou rho. So this rho will cancel, a will cancel, and this dou p upon dou rho is nothing but a square. So we'll get this u upon a. So Mach number is given by u upon a, where a is the speed of sound. So now we have to see how the shock wave is formed. So let's say there is flow is happening and there is one obstacle. So when fluid particle will collide with the obstacle, so this information will spread everywhere due to molecular collision. So this pressure waves are formed due to this information propagation, and this information propagation is more important in the upstream also. So when this flow is supersonic, its u is greater than a, then this pressure wavefront will meet this supersonic flow. So what will happen due to this? This all pressure waves will coalesce and create the strong wave, compression wave. This strong compression wave is only called the shock wave, which is formed ahead of the body. So what is shock wave? It is nothing but a gas dynamics discontinuity in which there is sudden increase in thermodynamics properties. Let's say there is one shock. So we consider it as a discontinuity. So let's say there is property 1 here, property 2 here. So there is sudden drastic change in properties. How does it form? Let's say there is one compression ramp. So due to this change in direction, this compression Mach wave will form, and these will coalesce and form a strong shock wave. If it is changing direction, if flow is moving away from itself, then this Mach wave will not coalesce and there will not be shock wave formation. Now let's see the flow past an aerofoil over a range of Mach number, mainly for transonic region, Mach number 0.8 to 1.1. Let's say Mach number is between 0.8 to 1. So initially the flow is subsonic, but due to geometry of aerofoil, at some point it will become supersonic. So due to the supersonic wave, as it is moving away from itself, there is supersonic flow. So due to the supersonic flow, there will be one shock wave in between the body, which will reduce its Mach number to less. It will make it subsonic again. But if let's say there is Mach number greater than 1, initially only, then one bow shock will form in front of the body. After that, flow will become subsonic, but again it can become supersonic on top of body, due to which there will be trailing edge shock will be there, which will make the flow in one direction again. Now we have to see what is hypersonic flow. So generally what flow which is greater than Mach number 1 is called the supersonic flow. But the hypersonic flow is generally associated with Mach number greater than 5. It is not like that when Mach number will become suddenly greater than 5, that flow will become hypersonic. It is not defined like that. There is some important characteristics corresponding to hypersonic flow. If those characteristics are happening in the flow, then even if Mach number is less than slightly 5 or greater than 5 also, it can be hypersonic flow can occur starting from that point also. And these hypersonic flow occur generally in the atmospheric re-entry of the space vehicle, or there is some long-range ballistic missile which will go out of atmosphere or on the rocket of high altitude, etc. So in the compressible flow, what happens that when there will be interaction of kinetic energy and internal energy of the fluid particle. So when the interaction is large, it can cause the excitation of vibrational energy mode, dissociation, recombination, chemical reaction, and even ionization of fluid molecules. Then the flow is called hypersonic flow. When Mach number is sufficiently large, then what can happen that due to this kinetic energy, which can be converted to its internal energy of the fluid particle, there can be other mode of energy which can be excited, which are vibrational energy, dissociation, recombination. There can be chemical reactions also. There can be ionizations also. If all these things are happening, then flow can be said to be hypersonic flow. So we can define one parameter beta, which is given by ratio of kinetic energy and internal energy. How is the kinetic energy given by? Half mu square, and internal energy is capital E, which can be written by m into specific energy. M can be removed, and E can be given by Cv into T for calorically perfect case. So we will get half u square upon Cvt, and for calorically perfect case, Cv can be written as Cv is nothing but R upon gamma minus 1. So it can be written as gamma minus 1 upon 2 u square upon RT. We can multiply gamma on numerator and denominator. So we'll get gamma minus 1 upon 2. This gamma RT is nothing but a square. So u square upon a square is what? Mach number square. So if let's say beta is increasing, so initially what will happen? There will be excitation of translation and rotational energy mode. So this is mainly for supersonic. And then excitation of vibrational energy mode will happen. For that there will be supersonic range, it will remain, but speed is increasing. Then if we increase the beta more, then there might be dissociation, recombination, and chemical reaction also happen. Here the flow will become hypersonic. If we increase the value of beta more, then there can be excitation of electronic energy modes, which will cause the ionization. So this is generally called hypervelocity. Now we will see some problem related to this beta. The ratio between beta, ratio of kinetic energy and internal energy for two flows occurring at m equal to 2 and m equal to 6 is given by assuming that gamma remain constant for both flows. Option A 9, option B 4, option C 16, option D 27. What will be the answer for this problem? Let's solve it. So beta is given by gamma minus 1 upon 2 m square. So let's say there are 2 m. So let's say beta 2 upon beta 1 will be given by this gamma portion will cancel. So we will get m2 square upon m1 square. So one Mach number is 6, which will become 6 square. Other is Mach number 2, p square. So it will be nothing but 36 upon 4, which is 9. So answer for this problem is option E, 9. Now we will see what are the flow characteristics which are common for hypersonic flow. So in hypersonic flow, there will be shock layer will be thin. So first is what is shock layer? Let's say there is one body and there is four shock around it. So the region between body and shock is called shock layer. So what will happen in the hypersonic flow? This shock wave will move closer to the body compared to supersonic flow. So due to which there will be thin flow region between the shock and body surface, which will be the thin shock layer. So why will it be so? When there is hypersonic flow, Mach number is high. So when Mach number is high and velocity, you can say that kinetic energy is high. More kinetic energy means at stagnation point, it will be converted to more thermal energy. You can think that high velocity is converting almost, it is coming almost to zero. It is converting more thermal energy. So more thermal energy means more temperature of the flow across the shock. So more temperature means density will be low. If we consider E equal to rho RT, if temperature is high means density will be low. Oh sorry. So I forgot to tell. Then across the shock, density will also increase and temperature will also increase. So density will be also high. So if there is very high density, it means that for same flow to pass through, we need a thinner region. So due to which the shock layer will be thin. The second characteristic is viscous dissipation. So what happens that inside the boundary layer, the velocity will become suddenly zero at the surface. So large amount of kinetic energy is converted to thermal energy due to viscous effect. So this lost kind of energy is transformed into the internal energy of the gas, which is called the viscous dissipation. And due to this enormous heating, the temperature will increase, so density will reduce inside the boundary layer. So due to the reduced density, boundary layer thickness will increase. And as the boundary layer thickness increase, the outside inviscid flow will be changed. You can think due to the effective body. And the change in inviscid flow outside will also change the affect the boundary layer of inside the flow. So there will be the interaction between the boundary layer and outside inviscid flow. So this is called the viscous interaction. This is also one of the important characteristics of the hypersonic flow. And at the high temperature, as mentioned below, that there can also be the recombination and dissociation. This kind of reaction can happen. So flow can become the chemical reactant, so which will alter the thermodynamic characteristics of the gas. For the assumption of calorically perfect gas, which we have used for supersonic flow, which we cannot use for hypersonic flow, because both Cv and Cp will depend on both pressure and temperature in hypersonic condition. So, and last point, let's say there is one body and there is fog. So if let's say there is one streamline which is passing through the normal portion of the curved surface, so there will be a larger increase in entropy. But if it is passing through the away section of the fog, weaker section of the fog, then there will be less increase in entropy. So there will be one entropy layer also inside the flow due to the strong entropy gradient. So, and this entropy layer wets the body for larger distances from the nose. It wets from the larger distances from the nose. Any doubt till now? Now we will see. Now we will do the revision of compressible flow. Basics of compressible flow, which will be useful in further of the course. First is the normal shock. So there are some assumptions which we take for the normal flow, which is that flow is steady. We consider the flow to be 1D flow. Flow is inviscid, but flow, let's say this is normal flow. So flow upstream and downstream of the flow will be the inviscid, but inside we consider that there is highly viscous part, due to which only the flow properties are changing drastically. We also assume that there is no external soft work and the gas is calorically perfect gas. The condition IS of gas is given by 1 and behind the shock it is given by 2, like P1, T1, ρ1, U1, P2, T2, ρ2, U2. Across the shock condition, P2, T2, ρ2 increases but velocity decreases, and the upstream Mach number will always be greater than 1. Downstream Mach number will be subsonic. So there are some governing equations related to that which we can find using the control volume method. Continuity equation is given by ρ1 U1 equal to ρ2 U2. Momentum equation is given by P1 plus ρ1 U1 square equal to P2 plus ρ2 U2 square. Energy equation is given by H plus U square upon 2 equal to constant, or H1 plus U1 square upon 2 equal to H2 plus U2 square upon 2. So let's say we know the condition at the state 1. What are the unknown? ρ2, U2, P2, H2. Now we have 3 equations and 4 unknown. So we need more equations. So we use the equation for enthalpy, H equal to Cpt. So we will get H2 equal to Cpt2 and H1 equal to C1 T1, Cpt1. So now what is more unknown? T2. But equation is still 4, so we will use one more equation of state, P equal to rho RT. So now we have 5 equations and 5 unknown. If we solve all these equations, we will get the normal shock relations, which is given by m2 square equal to 1 plus gamma minus 1 by 2 m1 square upon into m1 square upon gamma m1 square minus gamma minus 1 by 2. And m star is given by m star square equal to gamma plus 1 m square upon 2 plus gamma minus 1 m square. What is this m square? It is nothing but characteristics. M star is characteristic Mach number, which is given by u upon p star. Where p star is nothing but sonic speed at sonic state, and ρ2 by ρ1 is equal to u1 by u2 equal to gamma plus 1 m1 square upon 2 plus gamma minus 1 m1 square. For this characteristics Mach number, there is also one more relation, m1 star into m2 star equal to 1, which is nothing but Randall's relations. For preferred ratio, there is relation P2 upon P1 equal to 1 plus 2 gamma upon gamma plus 1 m1 square minus 1, or P2 upon P1 equal to 1 plus gamma m1 square upon 1 plus gamma m2 square. We know all these things, then we can find T2 upon T1 equal to P2 upon P1 ρ1 upon ρ2 from equation of state. Now we'll see some plots. First one is between Mach number for upstream and downstream Mach number. Second one is between entropy and upstream Mach number m1. This formula we got from that before we have derived one formula for entropy. Same formula we are using it here. So if we plot that f2 minus f1 upon r, we'll get this curve. From this curve you can see that for Mach number greater than 1, only we are getting f2 minus f1 greater than 0. Entropy is increasing only for this case, and entropy is decreasing for Mach number less than 1. So we can safely say that Mach number less than 1 is not possible for normal fog. There will not be any normal fog if flow is subsonic. Similarly, if we plot m2 and m1, we can get we can see that we are getting for m1 greater than 1 subsonic flow downstream, and m1 less than 1 supersonic flow downstream. But we already saw that m1 less than 1 not possible, so this is not possible. This is also not possible. Now we will solve one problem. A strong normal shock wave with pressure ratio of 29 across it is traveling into stationary air, gamma equal to 1.4 at T equal to 280 Kelvin in straight duct. See the figure. This figure. The magnitude of air velocity induced behind shock wave is, so here gas constant is given and some relation are given. We have to find what is this V. So how to solve this problem? So till now we have studied only the stationary software. Software was not moving. So first we have to make this software stationary, or write in coordinate frame such that software will become stationary. Let's say the velocity of this software is c. So if we add minus c everywhere, it will become stationary. The software will become stationary. So in this direction, let's say this is u1, u will become velocity c, and in this direction the u2 will become c minus v. Okay, so now first what is given? Pressure ratio is given 29. So pressure ratio, this is 1, this is 2. So P2 by P1 is given 29. And this T1 is given 280 Kelvin. So first we will find what is the Mach number here. You can see that for finding V, we should find U2 and U1. If we know U2 and U1, we can find C. So for finding U1, if we know the Mach number, then from the temperature, using the temperature, we can find U1. And this, if we know the Mach number, then we can also find density ratio from this formula. And using the rho1 U governing equation, rho1 U1 and rho2 U2, we can find the U2 also. So first we will use the pressure ratio formula, and so this P2 by P1 equal to 1 plus 2 gamma upon gamma plus 1, m1 is the minus 1. P2 by P1 is given 29, gamma is 1.4, you have to find m1. So this will become 28, 2.8 upon 2.4, m1 square minus 1. If we solve it, it will become 24. So m1 square will be 25. So m1 will be 5. Now if in the this rho2 upon rho1 formula we put m equal to 5, then you will get 1.4 plus 1 into 5 square upon 1.4 minus 1, 5 square plus 2. So this will become 2.4 into 25 upon 0.4 into 25 plus 2. This will come 60 upon 12, which will be 5. So rho2 upon rho1 is 5. We don't need this formula. So rho2 upon rho1 is 5. These two things we got. Now we also don't need this formula. So now we know that m1 equal to 5 and rho2 upon rho1 is 5. So what will the u1? u1 equal to m1 under root gamma r t1. m1 is 5, gamma is 1.4, r is 287, t1 is 3, t1 is 280. Sorry, t1 is 280. So if you put this value in the calculator, we'll get value of 16 we'll get value of 1677.08 meter per second. This is u1, and from rho 2 upon rho 1 we know that it is equal to u1 upon u2. So u2 will be equal to u1 upon 5, which is equal to 335.42 meter per second. Now if you see the figure here, C equal to u1, so u2 equal to u1 minus v, so v equal to u1 minus u2. So v equal to u1 minus u2. u1 is 1677.08, u2 is 335.42. So if we subtract it, we'll get 1641.66 meter per second. And round to the nearest integer, it will give 1342. Any doubt in the problem? Then we'll see what is oblique shock. Let's say flow is happening through the wedge when flow is turning toward itself, or there is one corner, concave corner, where also flow is turning toward itself. So then the shock wave which will form will be the oblique shock. As shown in the figure. Here also this is the discontinuity. Gas dynamics, discontinuity. Now we'll try to write the Gaussian equation for this oblique shock. So similar to before, let's say there is one oblique shock, and upstream it is given by 1, downstream it is given by 2. We will take some assumption like flow is steady. Here flow will be 2D because flow is turning. So let's say velocity v1 was in direction along x-axis, then v2 will be in the xy plane. Flow is invisible in state 1 and state 2, but in between the shock wave it will be highly invisible, highly viscous. Flow is also adiabatic flow. There is no addition of heat, there is no external shaft work, the gas is calorie perfect gas, and there is no body force. And the angle of shock wave is given by beta. And the flow turn angle is given by theta. So if the velocity was v1 and m1 before, and later v2 and m2, we can resolve the velocity as along the shock wave and perpendicular to the shock wave. So perpendicular to shock wave it is u1 and u2, along it is given by w1, w2. We can make one control surface like this ABCDEF to derive the governing equations. The governing equation is similar to normal shock. Only difference is that we have to take the normal component in all the equation used for the normal shock. So constraint equation is given by ρ1 u1 equal to ρ2 u2. Momentum equation is given by p1 plus ρ1 u1 square equal to p2 plus ρ2 u2 square. Energy equation is given by h plus u1 square upon 2 equal to constant. And enthalpy is given by h equal to cpt, and equation of state is given by p equal to ρrt. All equations are similar to normal shock. Only difference is that you have to take the normal component and one extra equation for tangential component. So first, this mn1 which uses this component u1. So how is u1 given? This angle is theta. So u1 is nothing but u1 sin theta. And if we write it in the terms of Mach number, this mn1 will be equal to m1 sin theta. Similarly, if you see this is angle theta, so this is beta minus theta, and we can get mn2 equal to m2 sin beta minus theta. So similar to before also, if ρ2 upon ρ1 equal to u1 upon u2, gamma plus 1 mn1 square upon 2 plus gamma minus 1 mn1 square. Here in the normal shock it was m1, now mn1. Similar relation for p2 upon p1 and mn2 also. m2 we can find from after finding mn2. So m2 equal to mn2 upon sin beta minus theta. Here one more extra relation compared to normal shock is the relation between theta, beta, m, because one extra unknown here is beta. Beta is extra unknown. We don't know the shock angle. So how to find the shock angle? Using the theta, beta, m relation. Which we have to solve numerically. And it is given by tan theta equal to 2 cot beta m1 square sin square beta minus 1 upon m1 square gamma plus cos 2 beta plus 2. And if we plot this equation, we will get this theta beta m diagram where it is plotted between shock wave angle beta and deflection angle theta for different Mach numbers. So for a particular Mach number and one deflection angle theta, we get a two solution of beta which correspond to weak shock and strong shock. Generally in the nature you will find the only weak shock, so we can directly use the weak shock relation, weak shock value of the angle. Now we will see one problem. An oblique shock is inclined at an angle of 35 degrees to upstream flow of velocity 517.56 meter per second. Deflection of flow due to this shock is 5.75 degree and temperature downstream is 182.46 Kelvin. Assume the gas constant R equal to 87 and specific heat constant gamma equal to 1.4 and specific heat of constant pressure Cp equal to 1005 joule per kg Kelvin. Using conservation relations, Mach number of upstream flow can be obtained as round off to 1 degree. How to solve this problem? Anyone know? First see what is given here. So shock angle beta is given 35 degree. Upstream velocity V1 is given as 517.56 meter per second. Theta is given as 5.75 degree. And T2 is given as 182.46 Kelvin. And other properties like R, Cp and gamma is given. So how can we find the Mach number? We can find directly from theta beta interrelations. If you know the theta beta interrelations, you can put all this and solve it immediately. This is the one way which you can find it yourself. As we are less on time, or you can directly use the theta beta m diagram also. Like if you know the theta 5.75 and beta 35, let's say 5.75 somewhere here and here is 35, you can match those lines and where it is meeting at which Mach number line, you can take that as the Mach number. Now we will see what is Prandtl-Meyer flow. If flow is turning away from itself, then it is called Prandtl-Meyer flow. Then we will get the Prandtl-Meyer wave. Let's say this is convex corner, so flow will come this way, it will go away from itself and it will form the Prandtl-Meyer wave. Initial wave will form the angle of mu1 with the flow direction and final wave will make mu2 angle with the downstream flow direction. So there are some assumptions like flow is steady, it will steady flow and it is isentropic flow. For normal shock and public shock it was not isentropic, but here flow will be isentropic. There is no external shock well and calorifically perfect case. So if we know the Mach number m1 and m2, we can get the initial wave angle, which is called Mach angle for both mu1 and mu2. So this mu1 is given by sine inverse 1 by m1 and mu2 is given by sine inverse 1 by m2. Now if we, let's say we know the m1, so we can find one Prandtl-Meyer function for this Mach number, which is mu m equal to under root gamma plus 1 upon gamma minus 1, tan inverse under root gamma minus 1 upon gamma plus 1 m square minus 1 minus tan inverse under root m square minus 1. and this angle theta 2, which is turn angle, is given by mu m2 minus mu m1. So let's say we know the m1 value, we can find further mu, then find the m2 using this Vandermeer function. And as we already know the flow is isentropic, after we get the m2, we can find all other flow properties within the isentropic relations. So what are the physical trends which we know in Vandermeer wave? That initial Mach number is upstream Mach number is always greater than 1, and temperature, pressure and density decreases across the Vandermeer wave, but Mach number increases. And as the flow is isentropic, total temperature and total pressure remain constant. So for general step of solving the problem is that first find mu1 or from Vandermeer function for Mach number m1. Then using the mu m2, using the theta 2 and mu m1, we find the mu m2. Then we can find m2 using the Vandermeer function for mu m2. Then rest of the properties can be found using the isentropic relations. Now let's see one problem. A trace from filtered photograph of the flow around the corner reveals the edges of expansion fan as shown below. The leading and trailing edges of the expansion fan make the angles as shown. Assuming gamma equal to 1.4, angle of expansion fan in degrees is Vandermeer function is given. So in this problem, we have to find this expansion fan angle. Let's give it a name phi. Okay. So first, let's say what is the mu1, Mach wave angle. This is mu1. So as this total angle is 180 degree, then mu1 is nothing but 37 degree. And what is mu2? mu2 is 20 degree. So now if we know the mu1 and mu2, we can find the m1 and m2. m1 is nothing but 1 upon sine mu1. So if we put this in the calculator, we will get Mach number equal to 1.66, mt equal to 1 upon sine 20 degree. Which will give Mach number of 2.92. So we know the m1 and m2. And if you see, this is angle theta. If we see this here, you can easily conclude that here we will see this is the mu1, this is theta, this is mu2, and this is phi. So we can see that mu1 plus theta equal to phi plus mu2. mu1 is 37 degree, theta we don't know, phi we don't know, and mu2 is 20 degree. So what is phi? Phi is 17 degree plus theta. So if we know the theta, we can find the phi. And what is theta? Theta is mu m2 minus mu m1. Now I already told how we got the m1 and m2. Just put this value m1 and m2 here, we will get mu m2 and mu m1. Using those, we can find the phi value. is left to you for the homework. Now we will see flow through the nozzles. So this flow through, let's say there is nozzle with its area is changing from A1 to A2. At surface 1, properties were P1, T1, U1, and surface 2, it was U2, P2, T2. So there are some assumptions like flow is a steady flow. It is quasi 1D flow. It is not 1D. Flow is adiabatic. There is no heat transfer. Flow is invisible, no external soft work, and calorically perfect gas. So we can get, if we take this control volume, we can get the governing equation, which can be written as like this. Continuity equation is given by rho1 u1 a1 equal to rho2 u2 a2. Momentum equation is p1 a1 plus rho1 u1 square a1 plus integration a1 a2 pdA plus p2 a2 plus rho2 u2 square a2. This term we are getting due to this area charge, this surface. Energy equation is similar to before, h plus u square upon 2 equal to constant, and rest of the equation is also same, enthalpy h equal to cpt and equation of a state equal to rho t. So if this equation are solved, we can get one area velocity relations, which is important, which is given by dA upon E equal to m square minus 1 du upon u. If m tends to 0, it corresponds to incompressible flow, for which you can get AU equal to constant. Now, first take for m greater than 1. For m greater than 1, this term will be positive. I write it here, dA upon A, m square minus 1 du upon u. This term will be positive. So if dA is greater than 0, then du will also be greater than 0. And if dA is less than 0, then du will also be less than 0. It means that if area is increasing, then velocity will increase. If area is decreasing, then velocity will decrease. M is less than 1, and dA upon A equal to m square minus 1 upon minus 1 du upon u. This term is negative for m less than 1. For if area is increasing, if this is positive, then this will be negative. If area is decreasing, then du will increase. It means if area is increasing, then velocity will decrease. If area is decreasing, velocity will increase. The same thing we can see from this flow. For Mach number less than 1, it means for subsonic flow, converging nozzle will give increment in velocity. For diverging nozzle, velocity will decrease. For Mach number greater than 1, divergent nozzle will give increment in velocity, and converging nozzle will give decrease in velocity. Any doubt till now? So if let's say there is converging divergent duct and there is subsonic flow before, then flow velocity will increase in the converging section and it will become Mach number equal to 1. After that, its velocity will again increase due to diverging duct. and it will become supersonic. But if let's say there is supersonic flow in the initially, then its velocity will decrease due to area is decreasing. Then its velocity will once again decrease because Mach number will become 1 and it will be in the supersonic range. From that area Mach number relation, if we solve it more, then we can get one area Mach number relation, which is given by A upon A star equal to 1 by m 2 upon gamma plus 1 1 plus gamma minus 1 upon 2 m square to the whole power gamma plus 1 upon 2 gamma minus 1, where A star is the area at Mach number equal to 1. First we plot Mach number and this area ratio A by A star. We'll get plot like this. So at any area ratio we'll get two solutions. One is subsonic solution, one is supersonic solution. And it depends on the back pressure condition in the nozzle and what kind of solution which we will get. So if A by A star is less than 1, then there will not be any solution for this problem. And all these things are written here, that if A by A star is less than 1, then there is no solution. And if A by A star is greater than 1, there are two solutions, one corresponding subsonic, one is supersonic, and it will depend on boundary conditions. Now we will see those boundary conditions. So let's say there is one reservoir here, and then there is the feed nozzle. Here pressure is P0. Here at the exit it is PP, and outside this is PV. So let's say initially this P0 is PV, then there will not be any flow. If we decrease this PV slightly, then flow will start, and at throat it will be some subsonic Mach number, then its velocity will increase in the converging section, then it will again start decreasing. So if we start decreasing this pressure more and more, we will get one at such point that at the throat Mach number will become 1. At that point it will become, we will get the maximum mass flow rate and nozzle will become choked, and this point is called the first critical point. And at this point the throat area will become A star, but after that also that back pressure is not sufficient for the supersonic flow. One more thing, that A by A star we have seen that there are two solutions. So for this pressure ratio there will be only subsonic solution at the throat, at the exit. So it will, so velocity will again decrease and it will become subsonic. This is the first critical point. Now corresponding to this, if pressure is very low, then there will be corresponding one third critical point, at which, so if pressure is very low, then corresponding to this there will be third critical point, at which the flow will be supersonic, corresponding to this area ratio. And in both these cases, flow will be isentropic throughout the nozzle. And at this condition, at third critical point, it is called the correctly expanded nozzle. And at the exit pressure, EV will be equal to PV in all these critical points. Now, if we from the first critical point, if we decrease the pressure more, then what will happen at the nozzle? It will remain choked. So at the nozzle, it will be Mach number equal to 1. So sub convergence section, it will remain constant as before. Only divergence section, as pressure is not low corresponding third critical point, there will be one normal shock, to which flow will become subsonic after that. And if we start decreasing this pressure more and more, this location of this normal shock will decrease, move towards the downward direction. And we'll get at one point where this normal shock will be just at the exit. So that point we will call the third critical point. So if you see that third critical point, this is P by P naught, one value. This is nozzle, throat, this is exit. So at exit, let's say this is E, then this ME1 and this is ME2. So this ME1 will be greater than 1 and ME2 will be less than 1. So before this shock, it will be fully supersonic solution corresponding to third critical point, but just after that it will be subsonic. So this is the third critical point. And this isentropic flow will be till this upstream of the shock. Now, if we decrease the pressure below this third critical point, but more than second critical point, the flow will become isentropic till this nozzle exit. After that, it is expanded more than required because pressure should increase to reach the back pressure. So there will be oblique shock at the end, which will increase the pressure. So there will be first oblique shock, then expansion wave to equalize the pressure. Then it will be the combination of oblique shock expansion wave like this, it will form. And if we started reducing the pressure below this second critical point, then as it is under expanded, there will be first expansion wave, then oblique shock like that to equalize the pressure at the back. And the flow is non-isentropic outside the nozzle. Now we will see one problem. A D-label nozzle is to be designed for an exit Mach number of 1.5. The reservoir conditions are given as P0 equal to 1 atmosphere, gauge T naught equal to 20 degrees Celsius, gamma equal to 1.4. Assuming shock-free flow in nozzle, the exit absolute pressure in atmosphere is in 3 decimal places. So P naught is 1 atmosphere gauge. So in atmosphere absolute pressure, how much it will be? 2 atmosphere. Why? Because absolute pressure is gauge pressure plus atmospheric pressure, and we will take 1 atmosphere as atmospheric pressure. So this is P naught. T naught is 20 degrees Celsius or 293 Kelvin, and ME is 1.5. So we have to find exit pressure. You can directly use the isotopic relations. This relation we can directly use. So it is by P naught by P B equal to 1 plus gamma minus 1 upon 2 ME square gamma upon gamma minus 1. We can put the value of ME, gamma, and P naught will get the PB. So we'll end our class here today. If you have any doubt regarding this, you can ask in the next class also, and we will meet next week at the same time. Thank you.